Bismillahirrahmanirrahim. Assalamu alaikum. In last class, we discussed about the Mobius function. Okay. In Mobius function, we discussed the definition of the Mobius function. Okay. The Mobius function is 1 when n is equal to 1 and 0 when n is divisible by a square of any prime, and minus 1 to the power k if n can be written in the product of distinct primes, okay, and where k is the number of prime factors. And we also discussed a result for a positive integer, okay, for any positive integer n, okay. So sum over the divisors of n, sum of the Mobius functions that runs over the divisors of n is either 0 or 1, okay. So 1 in the case when n is equal to 1 and 0 for all other cases, okay. So these results will be used in the Mobius inversion formulas. Okay. So Mobius inversion formula. Mobius inversion formula. Let f be a number theoretic function. Let f be a number theoretic function, and let fn equals sum that runs over the divisors of n, f of d, then. And we have already studied that if f is a number theoretic function or if f is multiplicative, but this is for any number theoretic function. Okay, if we have studied that if f is multiplicative, then capital F is also multiplicative. Okay. Anyway, the statement is then the number theoretic function fn is equal to the sum that runs over the divisors of n or the factors of n times mu d times f of n divided by d. Okay. Okay, now move to the proof of this result. Okay, it's given here that fn equals sum d that runs over the divisors of sum that runs over the divisors of n f of d. Okay. So if we replace this n by d, okay, in that case f n by d is equal to sum. So we have to write n by d here. Then we have to, because d is a demi variable or it's for the divisors. So here we are using we are using integer n by t, n by d is here as well. Okay, so we should use a different notation for the divisor. So we use d prime. So d prime that runs sum that runs over the divisors of n by t and d prime. Okay, so we just substituted n by d instead of n. Okay, and then we multiply both of the sides by mu d. It's the Mobius function. Fn by d equals mu d times sum d prime n by d f d prime. This mu of d can either be written inside the summation or outside the summation, because for the summation, for the sum, variable is, or dummy variable is d prime, and there is no d prime in mu d, so you can write mu d inside the summation sign. So you can write sum d prime over n by d mu d f d prime. Okay, so there is no problem to take either mu of d outside the sum sign or inside the sum sign. Okay, now take sum that runs over the divisors of n both sides. So mu d f n by d, that's we need it here. Okay, and then on the right hand side we will have double sum sign d runs over n, then we already have another sum d prime over n by d mu d and f d prime. Okay, so we need to show that the right hand side is equal to small f of n. Okay, we just need to show that. So here we know that d is the divisor of n, and d prime is the divisor of n by d. Okay, so if d runs over the n, then so d prime as well, because d prime runs over the divisors of n by d, so it means it runs over the divisor of n as well. Okay, if something is running over the divisors of n by d, then it must run over the divisors of n as well. Okay, because n by d is a factor of n as well. Anyway, so it means let me write something here. I should erase this. So it means d runs over positive divisors of n, then d prime also runs over the positive divisors of n. Okay, and then because d prime is the divisors of n by d, then d prime times d also divides. Also, d prime d divides n. Okay, because d prime is the divisors of n by d, so d prime times d must divide n. Okay, so there is no problem to interchange the notation that if we use d prime d prime can divide n, and d divides n by d prime. Okay, so now sum that d runs over n over the positive divisors of n, mu d f n by d is equal to sum. We can write d prime runs over the sum runs over the divisors of n, and another sum that runs over the divisors of n by d prime. So here we have two sums. One runs over the divisors of n, and the other one runs over the divisors of n by d. Similarly, here we also have two sums. Okay, one runs over the divisors of n, and the other one runs over the divisors of n by d prime. So in that case, we can write mu d f d prime. Okay, so for in last theorem that we discussed in last class, theorem 10, okay, so this sum is equal to 1 when n is equal to 1 and 0 otherwise, or for all the other cases. Okay, so we can because f d prime is related to d prime, so we can separate them. Okay, there is no problem to separate them. F d prime times sum n by d prime mu d. Okay, and we know that this sum is either 1 or equal to 0. Okay, so there is only one case when n is equal to 1. So this sum is 1, and in all the other cases this sum is equal to 0. Okay, so when n is equal to 1, this sum is 1, and for all the other cases this sum is 0. Okay, so consider the case where this sum is equal to 1. Okay, so in that case this value n by d square must be equal to 1. So we take n by d square equals to 1, which implies n equals to d prime. Okay. So when n equals to d prime, and all the other cases, this sum is 0, and 0 will be multiplied here, and the result will be 0. So we will have a long sum. Okay. In that, from that sum, we have to take only one value here, that will be 1. Okay, but all the other are 0, so we are considering that value, and that value is only possible when n is equal to d prime, because n by d prime is equal to 1. So in that case, sum d runs over the divisors of n, mu d f n by d is equal to sum, because d prime and n are same, so sum runs over the n fn times 1, because there is only one case, so there is no need to write some summation sign, so we must write f of n only. So that's the required case for the Mobius inversion formula. So this formula is called Mobius inversion formula, and there is another form of Mobius inversion formula as well. Okay. The other form of Mobius inversion formula is Fn. So this form is, let me write that form again, Fn equals sum d runs over the divisors of n, mu d f n by d. Okay. And the other form of Mobius inversion formula is sum runs over the divisors of n, mu n by d f d. They are same. Okay. So I am leaving this thing to show that two formulas are equivalent to you as an exercise. Okay. You can verify different things for, or you can verify these two formulas are same for different examples. Okay. But for in exercise, you have to prove this formula for the general case. Okay. And let me call Mobius inversion formula as theorem 11. Okay. Theorem 11. Next result, for the Euler phi function. So Euler phi function n for any integer n is n sum runs over the divisors of n, positive divisors of n, mu d over d. So by using this formula, you can find Euler phi function for any integer. Okay, look at the converse of theorem 11. In theorem 11, it is given that fn small f is a number theoretic function, and we assume that capital F of n is equal to sum that runs over the divisors of n, f of d. Then we have to prove that small f of n is equal to this. Okay. But the converse converse of this theorem will be when this condition is given and we have to prove this condition. Okay. So we call this result as theorem 12. Let f, capital F and a small f be number theoretic function number theoretic functions such that Fn equals sum runs over the positive divisors of n, mu d, capital F, and by d. Then we have to prove that capital Fn equals sum runs over the positive divisors of n, f of d. Okay. Now move to the proof of this result. Okay. By definition, f d equals sum. If you put d here, so we are just putting d here instead of n. So this will be d. So if you put d here and here, so we must change this d. So this will be d prime mu d prime. So d will be replaced by d prime and n will be replaced by d. Okay. So f d by d prime. Okay. Now take sum that runs over the divisors of n. So d runs over the divisors of n. F d equals sum that runs over the divisors of n. We already have another sum. D prime runs over, sum runs over the positive divisors of d, mu d prime, f d d prime. Okay. Now we can separate. Or because this is related to d prime, so we can use a bracket here. Okay. But yeah, that's runs for d prime. And here we have d over d prime. Anyway. So this is d over d prime. So for that we assume let d by d prime equals a new integer. Okay. Then this equation becomes sum runs over the positive divisors of n, f d equals sum d runs sum runs over the positive divisors of n, then again sum and because d by d prime equals k, so it means d is equal to kd prime. So we can also write kd prime equals d. Then mu d prime f k. Okay, now these two sums can be combined. Okay, because here we need divisors of n, and here we have kd prime equals d. Okay, because we have assumed that d by d prime equals to k, so it means we can use a single sum for both, that k d prime is a divisor of n, and we can write here mu d prime f k. Okay, so these two sums can be combined like that. And now, because k d prime is a divisor of n, so d prime is a divisor of n by k. Okay, so because d prime is related to mu d prime, so we can separate that sum dedicated to mu d prime. So if we write sum d prime, okay, is a positive divisor of n by k, so it means this sum runs over the divisors of n by k, and this is d prime. So d prime is related to mu d prime, so we can write like that. And we have fk. Okay, so then k is a divisor, because we have combined previously. Now we are separating for mu and k, f of k. So now we can write sum k that runs over the sum that runs over the divisors of positive divisors of n f k. Now we know that this value is either 0 or 1. Okay, so this value is either 0 or 1, so we can write sum k runs over the positive divisors of n f k. So this value is 1 when n is equal to k. Okay, so when n is equal to k, it means we can write n here. So if we write n here, so there must be n as well. So this will be f of n. That's the required result. Okay, at left hand side we have this. So it means f of n equals sum sum that runs over the positive divisors of n f of d. Okay, that's the proof of our required result. Okay, our next topic is quadratic congruences. We have already discussed linear congruences, okay, and systems of linear congruences as well. So now we will study about the quadratic congruences. Okay, so we should understand about the quadratic residues before going to the solution of quadratic congruences. Okay, let me introduce a simple or a general quadratic congruence, that is ax square plus bx plus c congruent to 0 modulo p. Okay, so that's the quadratic equation, and if quadratic equation is written in the congruence form, so this is called quadratic congruence over the modulo p. Okay, where p is a prime and this p must be the odd prime. So p must be odd prime and p does not divide a, because if p divides a, then the coefficient of x square becomes 0 in congruence. So this quadratic congruence will become linear congruence. Okay, so that's why we must have p must not divide a. Okay, and p is an odd prime. So if p is an odd prime, then p does not divide 4a as well. Okay, why 4a? Okay, we will discuss later. Okay, for example, we have this quadratic congruence. So let me multiply whole congruence by 4a. So that's why 4p does not divide 4a, because if p divides 4a, then the whole congruence will become 0. So 4a, or and then we will not be able to divide, to multiply by 4a both the sides if p divides 4a. So 4a times ax square plus bx plus c congruent to 0 modulo p. Okay, so now look at this quadratic expression. This quadratic expression 4a times ax square plus bx plus c can be factorized, or can be written like 4a square times x square plus 4abx plus 4ac. Okay, now we need to break the, or we need to make the perfect square formula. So if we want a perfect square formula, so we must have 2ax here. So we have here plus 2 times 2ax, then 2 times 2 is 4ax, then we need b here. Okay, then third term b square must be there, because we have to make perfect square formula, but b square is not here, so we have to subtract b square as well, and then plus 4ac. So we can use the perfect square identity here. So this will be 2ax plus b whole square, and then we take negative sign common from here. So b square minus 4ac. Okay. Now 4a times ax square plus bx plus c can be replaced by the difference of these two factors, two expressions. So this quadratic congruence becomes 2a x plus b whole square minus b square minus 4ac is congruent to 0 modulo p. Or you can write 2ax plus b whole square congruent to b square minus 4ac modulo p. Okay, and these values can be replaced by some other variables. For example, if you replace this thing by y, so this will become y square, and this is discriminant, can be replaced by b or a, whatever. So a modulo p. So any type of quadratic congruence in which p is not dividing 4a, p is an odd prime, and p is not dividing a, then that type of quadratic congruence can be reduced into the simpler form y square congruent to a modulo p. So there is no point to solve this type of quadratic congruence. So we always, because every quadratic congruence can be converted into this form, so we solve only this type of quadratic congruence, or any quadratic congruence can be converted into this. And then after computing the value of y, we'll be able to find the value of x by substituting, because uh, y is where y is 2ax plus b, and a is b square minus 4ac. Okay. Okay. If you look at the one example. Three x square plus 7x plus 5 is congruent to 0 modulo 13. Okay. Okay. So this type of congruence or quadratic can be converted into the simpler form, like y square is congruent to a modulo 13. Here we have 13, p is 13. So 13 does not divide 3, that's fine. 13 does not divide 4 times of 3, which is 12. Okay, that's fine, that's good. Okay, and the so these are the conditions, and 13 is odd prime as well. Okay, that's good. So we have to write, so A is 3, B is 7, and C is 5 here. So Y will be 2 times 3 times X plus 7. So this will be 6x plus 7. And a will be 7 square minus 4 times 3 times 5. Okay. 7 square is 49. 4 times 3 is 12. Okay. And 12 times 5 is 60. So 49 minus 60, which is minus 11. And minus 11 is congruent to 2 modulo 13, because we are working in modulo 13. So better to write, to use 2 instead of minus 11. Anyway, you can use minus 11 as well. So in that case, your quadratic congruence becomes y square congruent to 2 modulo 13. Okay. So now, how can we solve? We need to put values, okay, that gives you 2 as the remainder, okay, or 2 as the least residue. So if you put 1, you can't get 2 here. If you put 2 here, so you are taking y equals 1. So if y is equal to 1, then the y square is 1. So residue is not equal to 2. That is, let me use, this is y. So when y is 1, so residue is 1. When y is 2, so 2 square is 4. So again same 4. So when y equals 3, okay, and 0 is not the solution. Okay, it's clear from here that 0 is not the solution of quadratic congruence. So so for the case 3, okay, so 3 square is 9. So this is, the residue is 9 here. Oh, sorry, it's, let me, this is for 2 and this is for 3. And then for 4, if you put y equals 4, so 4 square is 16. And in that case, residue is 3. So, and then 5, 25, for 25, either you write minus 1 or 11. Okay. And then 6, for 6, 36. For 36, you need minus, for 36, minus 3 or 10. Then 7. 7 square is 49. For 49, 13 times 4 is 52. Okay. And 7 square is 49. That is, okay. So next is 8. So for 8 is 64. And 13 5 is 65. So 65, so it means minus. So this is this must be 12, I think. Yes, 12. So this is 12. For 9, so this is 3. For, because 5 square is 25 and 26 minus 1. So minus 1 means 12 in modulo 13. And then for 10, so for 10 is 9. For 11, is is again 4, and for 12 is 1, and for 13 is 0, either for 0 and for 13, so 0. So it means you can only put values from 0 to 12 in for modulo 13, and none of the value giving residue equal to 2, but we need 2 here. So no value of y satisfying this congruence. So it means this congruence is not solvable. So this congruence is not solvable. Okay. So let's have another example in which we will be able to solve the congruence. Okay. Okay, look at another example. 3x square minus 4x plus 7 congruent to 0 modulo 13. Same things. Okay. But we have a negative, instead of plus 7x, we have negative 4x and plus 7 here. Okay. Anyway, so what will be the value of y? So y will be 2ax plus b. So this will be 2 times 3 times x minus 4. So this will be 6x minus 4, and then a. So the value of a will be b squared minus 4ac. So b is minus 4. So minus 4 is squared minus 4. A is 3 and c is 7. So this is 16 minus 4 times 3 is 12, and or 3 times 7 is 21. 21 times 4 is 84. Okay. So 16 minus 84 is minus 58 and minus 68. So this is minus 68, and minus 68 can be written as plus 10 modulo 13. Okay. So now the congruence becomes y square congruent to 10 modulo 13. And we know that from here that where if we consider two values 6 and 7, so these two values are giving residues equal to 10, so which is required. So it means y equals 6 and 7 is a solution. Okay, so y equals 6 and 7 is a solution, but we need value of x, and we know that y is 6x minus 4, so we can substitute value of y here. So for y equals 6, we have 6 equals 6x minus 4. So this is 6 or 6x minus 4, and or you can write it's better to use congruence because it's a congruence. So is congruent to 6 modulo 13, and then 6x is congruent to 10 modulo 13. Okay, and for the other case, for y equals 7, so for y equals 7, 6x minus 4 is congruent to 7 modulo 13. So 6x congruent to 11 modulo 13. So that's the solution. 6x is congruent to 6x congruent to 10 modulo 13. So 6. Okay. 6 times 11 is 66. And 13 times 5 is 65. So the inverse of 6 is 11. So we can multiply by 11 both the sides. So 11 times 6x is congruent to 11 times 10 modulo 13. So 11 times, so this is x congruent to 110. 110. What is the meaning of 110 in modulo 13? 110 modulo 13 is 6. So 6 modulo 13. Then we multiply by 11 here as well. So 11 times 6x congruent to 11 times 11 modulo 13. And this is again x is congruent to 11 times 11 is 121. And 121 means in modulo 13, this is 4, because 13 times 9 is 117. So this is 121. So this is 4 modulo 13. So the solution is x congruent to 6 and 4 modulo 13. So that's the solution of the quadratic congruence. Okay. But this is this procedure of computing the quadratic residue is very difficult. Okay, so we will have the alternate procedure. We will discuss the other procedure, inshallah, in next class. Okay, uh, so in next class we will discuss the other techniques of computing the residues. Okay, and we will see the Euler criterion, okay, for the quadratic residues. Okay, thank you very much. Allah Hafiz.